A colossal stone pyramid rises from the desert, built with a precision that still defies explanation. Ancient builders achieved these engineering marvels without any modern tools, and you will discover exactly how they did it. We will uncover the forgotten technologies that moved mountains of stone and erected monuments lasting millennia. How did they cut and transport 100-ton blocks with such accuracy, and what knowledge was lost to time itself? What does it truly mean to build something that outlasts civilizations? The Great Pyramid of Giza consists of over 2 million stone blocks, each weighing an average of 2.5 tons. That is the foundational scale of this mystery. We are not talking about simple stone huts. We are discussing structures like the towering pyramids, the haunting stone circles of Stonehenge, and the silent, brooding Moai statues of Easter Island, carved from solid volcanic rock and moved across miles of terrain. These were projects that would be ambitious even with today's machinery, yet they were executed in eras devoid of steel tools, powered engines, or the advanced mathematical frameworks we take for granted. This is the core puzzle that captivates us. It fundamentally challenges a linear view of human progress. As one leading archaeologist noted, the enduring enigma is not just that they built these things, but that they achieved a level of precision we struggle to explain centuries later. Look at the common threads. Massive stone blocks, often weighing tens or even hundreds of tons, were quarried, shaped, and transported over vast distances. They were then assembled with astonishing precision. The Great Pyramid, for instance, is aligned to true north with an error of just a fraction of a single degree. Its base is almost a perfect square with sides that vary by mere inches. This is not rough construction. This is geometry and engineering executed with breathtaking accuracy. What does this profound capability reveal about the societies we often label as primitive? It suggests a deep, sophisticated understanding of the physical world, a knowledge that somehow allowed them to manipulate immense weight and achieve near-perfect alignment. To unravel how they did this, we must first look at the very substance they built with. The sheer scale of these monuments begins with a single block of stone. Picture an Egyptian quarry under the relentless sun, where teams of workers face a solid cliff of limestone. Their task is to free a block weighing several tons using tools that seem almost laughably simple by modern standards. This is where our first method comes into sharp focus, the mastery of stone quarrying. Before a single block could be moved, it had to be precisely extracted from the living earth. They used a combination of brute force and brilliant geology. Dolerite pounding stones, a rock harder than limestone, were swung tirelessly to crush the stone along a predetermined line. For finer work, they employed copper chisels. Though soft, they were effective when driven by muscle and persistence against the relatively soft limestone. But perhaps their most ingenious technique involved the power of water and wood. They would chisel deep channels around a block, then drive dry wooden wedges into the grooves. These wedges were then soaked with water. As the wood expanded with tremendous force, it would cleanly fracture the bedrock along the desired seam, isolating a perfect block. This method of channeling was a form of surgical precision on a massive scale, allowing them to carve out the very bones of the earth with control. The choice of stone was also a deliberate science. Builders were not just grabbing any rock they could find. They sought out specific types for their durability and aesthetic qualities. For the most imposing elements, like the massive obelisks and the inner chambers of pyramids, they journeyed to the quarries at Aswan, hundreds of miles up the Nile, to extract the beautiful and incredibly hard red granite. This stone was prized for its strength and striking appearance, a testament to their understanding of materials. The clearest window into this entire process is the unfinished obelisk, still lying in its Aswan quarry bed. This colossal monument, which would have been the largest ever erected, cracked during its extraction and was abandoned. It is a time capsule revealing the tool marks, the channel trenches, and the entire quarrying methodology frozen in stone. Looking at its immense form, still attached to the bedrock, you are forced to confront the monumental logistics. How did they plan such an operation, coordinating hundreds of workers to extract, shape, and prepare for transport a stone weighing over 1,000 tons? Understanding this first step, the sourcing of the material, reveals that the movement of these stones was not an afterthought. It was a challenge they engineered from the very beginning, designing the block in the quarry with its eventual journey in mind. Once a block was freed from the quarry, the real challenge began. Moving these stone giants across the landscape required more than just raw muscle. It demanded a clever application of fundamental physics, using tools so simple they are taught in school today, yet deployed on a scale that still inspires awe. This is the second method, the ingenious use of simple machines, primarily levers and the mighty ramp. Picture a multi-ton block of limestone resting on a wooden sledge at the base of a rising pyramid. Before it stands a colossal earthen ramp, an engineered mountain of mud brick and compacted earth, its slope carefully calculated. Teams of laborers, coordinated by shouts and signals, haul on thick ropes, their collective effort slowly dragging the sledge up the incline. This was the likely reality for the builders of the Great Pyramid. The ramp was their elevator, their crane, their essential tool for defeating gravity. At its core, this method relies on the power of the inclined plane. Pushing a heavy object straight up is nearly impossible, but pulling it along a gentle slope dramatically reduces the force required at any single moment. It trades a short, impossible lift for a long, manageable pull. Engineers who have replicated these techniques confirm their feasibility. The exact steepness of the ramp was critical. Too steep and the block becomes immovable. Too shallow and the ramp itself becomes an impossibly large construction project. The debate continues on the exact design of these ramps. Some argue for a single, long, straight ramp built against one face of the pyramid. Others propose a spiraling ramp that wrapped around the structure as it rose, a more economical use of material. There is also evidence for zigzag ramps that ran up one face and then switched back. For the stepped pyramid of Djoser, one of the earliest colossal stone buildings, archaeologists have actually found the remains of a massive ramp, providing tangible proof of this method in action. Alongside ramps, the lever was indispensable. A strong wooden beam and a sturdy fulcrum rock could transform a team's effort. By sliding the beam under a corner of a massive stone and pushing down on the long end, workers could lift the block just enough to slide logs or rollers underneath, allowing it to be shifted or pivoted with far less strain. This principle allowed a small force to control a tremendous weight. So how many people would it actually take to move a 2.5-ton block up a ramp? Experimental archaeology gives us a rough idea. On a well-lubricated sledge moving up a ramp with a manageable slope, it might have required a team of 20 to 30 strong individuals, all pulling in unison. This efficiency, however, came with a profound organizational requirement. It highlights the need for a massive, highly coordinated labor force, thousands of workers operating in shifts, all directed by a master plan. The simple machine solved the physics problem, but it was human organization that brought the solution to life. The sheer scale of the ramps and levers points to a third, equally monumental method, the mobilization of a vast and skilled labor force. Forget the outdated image of masses of slaves driven by the whip. The reality was far more sophisticated. At Giza, archaeological discoveries have revealed entire towns built for the pyramid workers, complete with bakeries, breweries, hospitals, and barracks. These were not prisoners, but likely skilled artisans and farmers who worked on the monuments during the annual flooding of the Nile, when their fields were underwater and agricultural labor was impossible. The state provided them with a steady diet of bread, beer, and fish, evidence found in the remains of their meals. One archaeologist who has spent decades excavating these worker villages puts it this way: the bones we find show these men had access to good medical care, and their remains tell a story of a well-fed, organized community, not an oppressed one. This was a national project, a massive, coordinated effort that harnessed the entire society. The actual movement of the stones was a symphony of coordinated power. Oxen would have been used for the heaviest loads, their immense strength pulling wooden sledges. For the final, precise positioning, it came down to human muscle. Imagine a massive stone block on a sledge with rows of rope teams stretching out before it. A foreman might have called out a rhythm, a chant to synchronize the pull of dozens or even hundreds of workers. An ancient Egyptian relief actually shows this, depicting a colossal statue being towed by a huge crew, with a man standing on the statue itself pouring a liquid, likely water, onto the ground in front of the sledge to act as a lubricant and reduce friction. This single image captures the entire system, the coordination, the simple physics, and the immense human effort all working in concert. Reflect for a moment on the social organization this required. To feed, house, and direct thousands of people for decades on a single project required a level of administration and logistics that rivals any modern corporation. This was a civilization that had mastered not only stone but also the management of humanity itself. With so many hands pulling in unison, the next question becomes one of delicate control. How did they guide these multi-ton stones into positions so precise that a knife blade cannot slip between them? That immense human force could move mountains of stone, but raw power alone could not achieve the breathtaking precision we see today. The true magic unfolded in the final stage, the meticulous art of shaping and dressing each block. After a stone was hauled to the site, skilled craftsmen took over. Working with what we would consider primitive tools, they transformed rough-hewn blocks into perfectly flat, seamless components. For softer stones like limestone, they used dolerite hammers and copper chisels to chip away the surface, patiently pecking and grinding until it was smooth. But for the hardest stones like granite, they employed a different kind of genius, the power of abrasion. They would rub the granite surfaces with a slurry of quartz, sand, and water. Quartz is harder than granite, so this simple mixture, applied with endless patience, acted like a modern diamond-tipped saw, slowly grinding the stone down to a perfectly flat plane. This same abrasive technique, using wet sand and a taut cord or a copper blade, allowed them to cut through massive stone blocks. It was a slow, deliberate process, but it yielded an edge so precise it looks machined. The evidence for this is etched into history. Look at the polygonal walls of Sacsayhuamán in Peru. Here, massive stones are carved into complex, irregular shapes that interlock like a three-dimensional puzzle. Each block was individually shaped to fit its unique neighbors, with no two joints alike. This was not just for show, it created a structure incredibly resistant to earthquakes. An archaeologist specializing in these techniques notes that dressing a single granite block to such a perfect fit could take a single worker many months. This was not brute labor, it was the work of master artisans. The final step was the fitting. Masons would place a block next to its intended neighbor. They would then identify the high spots, often by coating one surface with red ochre and tapping the two stones together. The pigment would transfer to the high points on the opposing block, telling the craftsman exactly where to grind next. They repeated this process again and again until the two surfaces met perfectly, creating those legendary joints so tight that not even a razor blade can slip between them. This painstaking process raises a profound question for our modern world of instant results. What does it mean to invest not just days, but years of skilled labor into a single stone, trusting that your work will outlive you by millennia? That level of precision did not come from guesswork. It points to a deep and sophisticated understanding of geometry and measurement, a system of calculation that guided their hands from the quarry to the final, perfect fit. That level of precision did not come from guesswork. It required a fifth, deeply sophisticated method, a mastery of measurement and alignment that connected the earth to the heavens. The Great Pyramid of Giza presents us with a fact that borders on the impossible. Its four sides are aligned to the four cardinal directions, north, south, east, and west, with an error of just 1/15 of a single degree. To put that in perspective, that is more accurate than the alignment of the Royal Observatory in Greenwich, London, a building constructed with modern telescopes and technology. So how did an ancient civilization achieve such perfect orientation without GPS or laser theodolites? They looked up. The night sky was their ultimate reference point. They likely used an instrument called a merkit, a simple device consisting of a palm rib with a slit cut in it, attached to a plumb line. An astronomer priest would sight a specific star through the slit as it rose or set, while an assistant marked its position on the ground with stakes. By tracking the circular path of stars around the celestial pole over many nights, they could establish a true north-south axis with astonishing accuracy. This was not just about building a stable foundation. It was about anchoring their most sacred structures to the eternal order of the cosmos. The mathematical knowledge embedded in these structures is equally profound. The ratio of the Great Pyramid's perimeter to its height is very nearly 2 times pi, the mathematical constant that defines the relationship between a circle's circumference and its diameter. This suggests the builders might have understood this fundamental concept long before it was formally defined in Greece. Historians debate whether this was intentional or a byproduct of their chosen slope and measurement system, but the coincidence is remarkable. It points to a geometric intuition that was deeply woven into their architectural philosophy. On the ground, this celestial and mathematical knowledge was translated into reality with shockingly simple tools. To lay out the massive, perfectly square base of a pyramid, they probably used long, knotted cords and wooden stakes. They could create perfect right angles using a simple loop of rope with 12 equally spaced knots. By stretching this rope into a 3-4-5 triangle, they created a perfect 90-degree corner, a principle still taught in geometry classes today. This method of using cords and stakes could scale up almost infinitely, allowing them to project a perfect geometric design across acres of desert. This mastery of alignment was a global phenomenon. At Stonehenge in England, the entire monument is oriented towards the rising sun on the summer solstice. The massive heel stone stands directly in the path of the sun's first rays on the longest day of the year. This was not a random placement. It was a deliberate, carefully calculated act that required years, perhaps generations, of precise astronomical observation. Can you conceive of the patience required to plan such a thing, to watch the sun's slow drift across the horizon for decades, marking its extreme positions until you were certain of its path? This deep connection between sky and stone reveals a fundamental truth about these ancient builders. Their greatest monuments were not just buildings. They were calendars, observatories, and models of the universe, all constructed with a geometric language that we are only now beginning to fully decipher. A canal stretches into the distance, its calm surface belying the immense weight it supports. A massive barge laden with a stone colossus glides silently toward its destination. This was the sixth method, the strategic mastery of water, which transformed an impossible land journey into a manageable voyage. For civilizations like the Egyptians, rivers were not just sources of life, they were the world's first and most efficient highways. The annual flooding of the Nile was not a disaster to be endured, but a seasonal tool to be harnessed. As the floodwaters spread across the land, they created a network of temporary channels, allowing heavy barges to be floated much closer to the desert construction sites than was possible during the dry season. This was logistics on a grand scale. They did not just use the river, they engineered it, digging canals directly from the Nile to the foot of the rising pyramids, creating a permanent water route for stone delivery. The scale of these waterborne operations is almost unimaginable. Consider the transport of the obelisk of Hatshepsut, a single shaft of red granite estimated to weigh over 1,000 tons. How do you even load such a monument onto a boat? The likely method involved brilliant, patient engineering. They would have first constructed the barge itself in a deep, specially dug basin next to the quarry. Once the obelisk was ready, they would maneuver it onto earthen embankments surrounding the barge. Then, they would breach the temporary dams holding back the river, allowing water to flood the basin and float the barge, lifting the obelisk from its cradle in a seamless, fluid motion. The journey itself was a feat of navigation, with teams of smaller boats guiding and towing the colossal barge downstream. But the true, heart-stopping moment must have been the unloading. How do you safely bring a 1,000-ton stone from a floating, unstable platform onto solid ground without catastrophic damage? This reverse process, guiding the obelisk onto another prepared ramp as the water was slowly drained from the basin, required a level of coordination and control that pushes the boundaries of ancient engineering. Beyond transportation, water served another critical function on the construction site itself. Before a single stone was laid for a pyramid's foundation, the ground had to be perfectly level. How do you achieve a perfectly flat plain across acres of uneven desert bedrock? The answer lies in a simple network of trenches. They cut shallow channels into the rock in a grid pattern, then filled them with water. Using the immutable law that water always finds its own level, they could mark a consistent height on the sides of all the trenches. By cutting the bedrock down to these markers, they created a foundation that was leveled to within a fraction of an inch across its entire vast expanse. It was a tool of breathtaking simplicity and accuracy, turning a fundamental property of nature into a master builder's instrument. This clever manipulation of liquid, from floating mountains of stone to scribing perfect plains, showcases a profound partnership with the natural world. Yet to control these elements, they relied on another material, one that is often overlooked in these stories of stone. The strength of stone was matched only by the ingenuity of wood. You can almost hear the groaning of massive wooden sledges as they inch forward, their immense loads shifting on a pathway slick with water and mud. While stone survives for millennia, wood was the silent, perishable partner in this ancient engineering, a material whose temporary nature has erased much of the evidence for its crucial role. The construction of these sledges was itself a feat of carpentry. They were not simple platforms, but robust, engineered frames designed to distribute the tremendous weight of a multi-ton block, often lashed together with ropes made from papyrus or other strong fibers. To move these loaded sledges, workers placed round wooden logs as rollers underneath. As the sledge was pulled forward, the rollers would travel with it, and laborers at the back would constantly retrieve the freed rollers and run them to the front, creating a continuous, moving track. This method dramatically reduced the friction, turning a near-impossible drag into a manageable, if painstakingly slow, haul. For vertical lifts, wood was again the answer. The Egyptians used a simple but effective lever and fulcrum system, and later the shaduf, a counterweighted crane for lifting water, demonstrated the principle of leveraging weight. The Romans would later perfect this with the treadwheel crane, a massive wooden wheel powered by men walking inside it, like a human-powered hamster wheel, to hoist heavy stones high into the air for their temples and amphitheaters. The key to making any of this work was reducing friction to an absolute minimum. Tomb paintings and archaeological evidence confirm what seems almost too simple. They poured water or laid down a slurry of wet mud in front of the sledge's path. An expert in ancient technology points out that these depictions are not symbolic, they are literal manuals. The liquid acted as a lubricant, mixing with the desert clay to create a slick surface that could cut the pulling force required by half. This simple act of pouring water transformed earth into a slipway. This principle of wooden leverage might even explain one of archaeology's greatest puzzles, the Moai statues of Easter Island. A compelling theory suggests these giants were not dragged horizontally, but were instead walked upright to their platforms. Teams would have used ropes to rock the statue from side to side, carefully pivoting it forward with each rhythmic pull, effectively making the statue walk itself across the island. It was a dangerous, coordinated dance that used the statue's own weight and momentum, all controlled by ropes and wooden levers. Consider for a moment the sheer volume of timber required for these projects. Every sledge, every roller, every crane represented trees, entire forests that were harvested to serve these monumental ambitions. The temporary nature of these wooden machines reveals a profound truth. These builders were masters of temporary infrastructure. They designed entire systems, from floating harbors to massive lifting devices, knowing they would be dismantled and forgotten, leaving only the eternal stone to tell their story. The Great Pyramid did not spring fully formed from the desert sand. It was the ultimate expression of a learning process that spanned centuries, an eighth method built not from stone but from knowledge itself. Each colossal monument we marvel at today represents the pinnacle of a long architectural evolution, a story of trial, error, and relentless refinement passed from one generation to the next. Before the smooth, perfect slopes of Giza, there was the step pyramid of Djoser. This revolutionary structure, the world's first major stone building, was a bold experiment. Its architect, Imhotep, stacked 6 mastaba tombs of decreasing size on top of one another, creating a staircase to the heavens. It was a monumental proof of concept, demonstrating that large-scale stone construction was possible. But it was also a lesson in what not to do. The techniques were still being figured out. The core was built with rough, small stones, and the entire structure was originally intended to be a flat mastaba before being expanded vertically, showing a design that evolved even during construction. The learning curve is starkly visible at the site of Maydam. Here, what began as a step pyramid was later modified into a true, smooth-sided pyramid. But the chosen angle was too steep, and the outer casing, built on unstable sand, eventually collapsed in a catastrophic landslide. The ruins stand today as a silent, powerful teacher. Archaeologists studying the site believe the collapse was a pivotal moment, a dramatic failure that forced engineers to reassess their methods. They learned about the critical importance of a stable foundation and the dangers of an overly ambitious slope. This hard-won knowledge was directly applied to the next project, the Bent Pyramid at Djoser. Its builders began with the same steep angle as Maydam, but halfway up they visibly changed their minds, reducing the angle to a more stable incline. You can see the correction in its distinct bent profile, a permanent record of a mid-construction course correction born from the memory of a previous disaster. This pattern of iterative learning was a global phenomenon. In Mesopotamia, builders experimented for centuries with mud brick and baked brick, developing the corbel arch long before the true, self-supporting Roman arch was conceived. They would stack bricks, each layer projecting slightly beyond the one below, until the two sides met at the top. It was a less stable design, but it was a crucial stepping stone, a fundamental lesson in spanning space that would be perfected by later cultures. Across the ocean, the Maya of Mesoamerica show a similar progression. Their earliest temples were modest mounds. Over generations, they grew in scale and complexity, with each new layer of construction encapsulating the lessons of the past, creating the massive, intricate pyramids like the one at Tikal. What does this long history of failure and revision tell us about our own relationship with progress? We often celebrate only the final, flawless triumph, forgetting the essential, messy journey of experimentation that made it possible. This accumulated, hard-won knowledge was worthless, however, without a system to preserve and implement it. That system was the ninth method, the invisible architecture of a highly organized society. The true scale of these projects becomes clear when you visualize the construction site not as a chaotic mob, but as a meticulously organized machine. This ninth method, the invisible architecture of complex social organization, is what transformed grand visions into stone and mortar. It was a system of specialized teams, each with a precise role, from the quarrymen who extracted the stone to the transporters who moved it, the masons who shaped it, and the overseers who coordinated it all. The administrative genius required to manage this operation for decades is, in many ways, as impressive as the engineering itself. Consider the basic human needs. Feeding thousands of workers on the remote Giza plateau was a logistical nightmare solved with stunning efficiency. The state established bakeries and breweries capable of producing thousands of loaves of bread and jugs of beer daily, alongside a steady supply of fish from the Nile and meat from cattle herds. One archaeologist who has studied the worker settlements explains the challenge. Supplying a remote desert site with enough food and water for a permanent workforce of thousands was an achievement that rivals the pyramid's construction. It required a supply chain that stretched the entire length of Egypt. This immense effort was managed by a rigid hierarchy of officials. Tomb inscriptions and surviving clay tablets from other sites detail this chain of command, from the vizier, the pharaoh's right hand, down through chief engineers, scribes who kept meticulous records, and gang foremen who directed the laborers on the ground. We even know that work crews were organized into competing teams with names like the Friends of Khufu or the Vigorous Gang, fostering a sense of identity and camaraderie that boosted morale. This breakdown of tasks into manageable, synchronized units is the very essence of modern project management. Think of the skills you use to coordinate a team at work or to plan a complex event. The ancient builders were doing the same thing, but on a civilization-wide scale and without digital tools. This principle of large-scale coordination extended far beyond Egypt. The Roman aqueducts, for instance, required precise planning across vast territories. Teams of surveyors, engineers, and laborers had to work in concert to channel water from distant mountain springs into cities, maintaining a consistent, gentle downhill slope for dozens of miles. This was not a single project, but hundreds of interconnected ones, all demanding the same sophisticated management of resources, time, and human skill. This level of organization, however, could not exist in a vacuum. It was entirely supported by a robust economic system that fueled the entire monumental endeavor. That immense organization required a constant, life-sustaining river of resources flowing to the construction site. The 10th and perhaps most fundamental method was the creation of a sophisticated economic system, a machine for collecting and redistributing wealth on a scale that could fuel decades of monumental labor. These projects were not just built with stone, they were built with grain, timber, and copper, all flowing from the farthest reaches of a kingdom to a central point as a form of taxation or tribute. The entire economy was harnessed to a single, colossal purpose. In ancient Egypt, the pharaoh's power was absolute, and his divine mandate to build an eternal tomb was the ideological engine that drove this economic machine. Farmers, who formed the vast majority of the population, paid their taxes not in coin but in a portion of their harvest. This grain, collected in massive state granaries, became the literal bread and beer that fed the army of workers. The agricultural miracle of the Nile Valley was the true foundation of the pyramids. The river's predictable flooding created incredibly fertile land, yielding a surplus of food. This surplus was the key. It meant that not every person had to farm to survive. It freed up a large segment of the population, particularly during the inundation season when the fields were underwater, to work on state projects. An economic historian specializing in ancient states explains that this redistribution of agricultural wealth was the primary mechanism. The state took the surplus and used it to support specialists and laborers who were not producing their own food, enabling them to build for the state full-time. This system of centralized storage and distribution is visible in the archaeological record. Near the great temple complexes of Mesopotamia, archaeologists have uncovered the remains of enormous granaries and storehouses. These were the ancient equivalent of central banks, holding the grain, oil, and textiles that formed the wealth of the state, ready to be paid out as rations to workers and officials. This model of a labor tax was perfected by the Inca Empire with their mitas system. Every household across the vast empire was obligated to contribute labor to the state for a certain number of days each year. This labor built and maintained the incredible network of roads, terraces, and monumental structures like Machu Picchu. It was a rotating, mandatory public service that built the infrastructure of an empire without the need for money. This raises a profound question for us today. Our modern societies undertake their own mega projects, from sprawling space programs to vast internet infrastructures. What do these colossal investments of collective wealth and effort reveal about our own societal priorities and the ideologies that drive us? Just as the pyramids proclaimed the divine power of a pharaoh, our greatest projects are monuments to our own values, whether they be scientific discovery, global connectivity, or national pride. The funding and supply of these ancient endeavors were always justified by a powerful driving ideology, a shared belief that gave meaning to the immense sacrifice. A pharaoh did not order a pyramid built out of mere vanity. He was commissioning a cosmic engine, a machine of stone designed to propel his soul through the heavens and ensure the eternal balance of the world. This 11th method, the driving force of religion and ideology, was the invisible fuel that powered the entire monumental endeavor. Without this profound spiritual imperative, the decades of labor, the immense economic cost, and the sheer will required would have been unimaginable. These structures were anchors between the earthly and the divine. Their alignments with the sun, the stars, and the cardinal directions were not just feats of engineering. They were acts of worship, physical prayers etched into the landscape. The ancient Egyptian pyramid texts, some of the oldest religious writings in the world, speak directly to this purpose. One spell proclaims, "The king ascends to the sky among the stars. He navigates the celestial ocean." The pyramid was his launch vehicle, its smooth, gleaming sides a ramp of sunlight for the pharaoh's spirit to climb. This belief system provided the ultimate justification for marshalling an entire civilization's resources. The desire to honor a god or deify a ruler created a purpose so powerful it could sustain a project for generations. Look at the Parthenon in Athens, perched high on the Acropolis. It was a temple to the goddess Athena, a breathtaking home for a divine patron, but it was equally a bold statement of Athenian power, wealth, and cultural superiority, an ideological declaration carved in marble for all the world to see. Its perfect proportions and sacred geometry were not just aesthetically pleasing, they were believed to reflect the divine order of the universe itself. This spiritual drive was the true project manager, the force that convinced thousands to contribute their labor, not as coerced slaves, but as participants in a sacred duty that guaranteed cosmic and social stability. It makes you wonder what shared belief, what unifying ideology in our modern world possesses the power to mobilize a society for a project spanning 50 years. Is it the pursuit of scientific knowledge, the preservation of our planet, or the dream of reaching for the stars? These ancient builders encoded their deepest truths not in books, but in the very angles and alignments of their stone canvases, creating a sacred geometry that spoke a silent, powerful language. That principle of lubrication turns a near-impossible drag into a manageable pull, but moving a megalith across miles of varied terrain presented a cascade of other intricate problems. The real challenge was not just reducing friction, but creating a stable, moving pathway for the sledge itself. This is where the method of log rollers comes into sharp focus. Imagine a team of workers, their movements synchronized like a well-rehearsed dance. As the heavy sledge is pulled forward, it rolls on a bed of sturdy, round logs placed perpendicular to its path. The moment a log emerges from the back, a laborer quickly retrieves it and runs it to the front, placing it down to continue the track. This creates a continuous, rolling conveyor belt made of wood, allowing the sledge to inch forward in a surprisingly efficient manner. It was a simple solution, but its execution required flawless timing and a large supply of timber. Experimental archaeology has proven this method's effectiveness beyond theory. In one famous modern experiment, a team in Japan successfully moved a multi-ton concrete block using only log rollers, ropes, and human power. They found that the key was not just strength, but rhythm, with a designated caller setting the pace for both the pullers and the roller crew. A misplaced log or a moment of miscommunication could halt the entire operation, or worse, cause the immense stone to shift dangerously. These experiments reveal that the true engineering marvel was not the tools, but the human coordination that made them work. To make this grueling journey smoother, builders often prepared the very ground they traveled on. For the pyramids at Giza, there is compelling evidence of paved limestone roads, their surfaces worn smooth by the passage of countless sledges. These were not mere paths but engineered trackways, designed with a slight trough or with wooden rails on either side to guide the sledges and prevent them from sliding off course. They invested immense effort into building this temporary infrastructure, knowing it would pay off in the safety and speed of transporting thousands of blocks. A stunning example from a much later era proves the enduring power of these ancient techniques. In 18th century Russia, the task of moving the Thunderstone, a colossal granite boulder intended as the pedestal for the bronze horseman statue, seemed insurmountable. The stone weighed an estimated 1,500 tons. Engineers of the time, lacking modern machinery, looked to the past. They employed a massive bronze sledge resting on a path of bronze spheres rolling in a track, a sophisticated variation on the log roller. Teams of men, coordinated by drumbeats and signals, inched the monolith forward for months during the winter, using the iced over ground to their advantage. This project, though centuries removed from the pyramids, demonstrates the same fundamental principles: patient coordination and clever physics overcoming immense weight. Can you fathom the sheer trust required for every person involved in that operation? Each pull of the rope, each placement of a roller, had to be perfectly synchronized with hundreds of others, a symphony of human effort where a single mistake could mean catastrophe. Guiding a stone across the land was a monumental achievement, but it was only the first half of the struggle. Once it arrived at the sacred site, the even more delicate task of raising it skyward began. The final act of construction demanded a different kind of courage. After a stone's long journey across land and up ramps, the most delicate and dangerous task remained: lifting it into its precise vertical position. Think of the massive lintel stones at Stonehenge, each weighing 25 tons, needing to be hoisted 20 feet into the air to rest perfectly atop the towering uprights. Or picture the final capstone of the Great Pyramid, a solid piece of gold or electrum, being secured at a dizzying height of nearly 500 feet. How did they achieve this final, gravity-defying lift without cranes? The theories are as ingenious as they are varied. For the pyramids, the most accepted method involved the continued use of those massive ramps, but on a much steeper and narrower scale. A final direct ramp may have been built right up to the apex, allowing workers to drag the capstone to the very top. For structures like Stonehenge, a different technique likely came into play, one that relied on levers, ropes, and a profound understanding of balance. One compelling method is known as cribbing. Workers would first tip the stone into a prepared hole, but not all the way. They would use massive levers to raise one side of the stone just enough to slip wooden logs or blocks underneath. Then they would raise the other side, adding more blocks. This slow, incremental process, like jacking up a car with a stack of books, would gradually walk the stone upward until it was standing upright. To place a horizontal lintel on top, they might have built an earthen ramp against the uprights and dragged the lintel up, or they may have used a wooden frame as a primitive crane. A team would pull down on ropes running over the top of the frame, leveraging the stone upward in a slow, controlled arc until it could be nudged into place. Engineers who have modeled these techniques confirm they are entirely feasible with the materials available. The real challenge was not the physics, but the nerve. Every lift was a high-stakes ballet. The ropes, made of natural fibers, could fray. A wooden lever could snap under the immense strain. A single misstep in the coordinated pulling could send a multi-ton stone crashing down, undoing years of work in an instant. The precision required for the final placement is what truly stuns the modern mind. Consider the principle of the keystone in arch construction. Each stone in an arch is carefully carved into a wedge shape. They are all supported by a temporary wooden frame until the very last stone, the keystone, is hammered into the center at the top. This single piece locks all the others into place, and the entire structure becomes self-supporting, capable of bearing immense weight for millennia. That final, decisive tap of the hammer was the culmination of countless hours of precise carving and alignment. One wrong angle and the arch would collapse. So what kind of mindset did these final acts demand? It was a blend of unwavering patience, absolute trust in your fellow workers, and a quiet confidence that the calculations made on the ground would hold true in the air. This meticulous process of lifting and locking stones into place leads us directly to the hidden genius that held it all together, the invisible strength of the joints themselves. The strength of a wall lies not in its mortar, but in the perfection of its joints. This principle reaches its absolute zenith in the dry stone construction of the Inca. High in the Andes, their walls stand as a testament to a 14th method, an almost supernatural mastery of joining that required no binding agent whatsoever. At sites like Sacsayhuamán and Ollantaytambo, massive stones, some weighing hundreds of tons, are carved into complex, irregular polygonal shapes. They fit together so perfectly that you cannot force a single piece of paper between them. This was not an aesthetic choice, it was a profound engineering solution for one of the most seismically active regions on Earth. When an earthquake strikes, a rigid mortar-bound wall will crack and crumble. But an Inca wall, with its intricate, interlocking joints, dances. The stones shift and settle against each other during a tremor, absorbing and distributing the immense energy, and then settle back into place once the shaking stops. They have done so for centuries, outlasting every colonial structure built upon their foundations. The process of creating such a wall was a monumental puzzle. Masons would first roughly shape a block at the quarry. Once it was transported to the site, the real artistry began. They would position it next to its intended neighbors and begin the painstaking work of dressing the contact surfaces. Using harder stones as hammers and abrasive sand, they would grind the granite surfaces down, constantly testing the fit. They used a method similar to the red ochre technique, where a colored paste would be applied to one stone. When it was tapped against its neighbor, the high spots would be marked by the transferred pigment, telling the mason exactly where to grind next. Each block was custom shaped for its unique position, with all its neighboring stones in mind. The result is a chaotic-looking jigsaw of immense weight that is, in reality, a perfectly balanced monolithic structure. This concept of joining massive stones was pursued with different materials across the ancient world. Greek architects working with marble often used bronze cramps. They would carve out swallowtail-shaped channels in the opposing faces of two stone blocks. A heated bronze clamp would be fitted into this channel, and as it cooled, it would contract, pulling the stones tightly together. The joint was then sealed with molten lead to prevent the bronze from corroding. The Romans employed a similar technique, sometimes pouring molten lead directly into dovetail slots to lock stones in place, creating a powerful, rigid bond for their temples and amphitheaters. Perhaps the most staggering example of megalithic joining is the trilithon at Baalbek in Lebanon. Here, 3 limestone blocks, each weighing over 800 tons, are positioned side by side with such precision. They form the foundation of a Roman temple, but their origin and method of placement remain one of the greatest unsolved mysteries of engineering. The joints between these behemoths are as tight as any Inca wall. Can you fathom the mindset of the masons tasked with shaping the ends of an 800-ton block? A single miscalculation, an angle ground a fraction of a degree off, and the block would be useless, an eternal monument to failure. This global pursuit of the perfect joint, from the Andes to the Mediterranean, reveals a universal truth. The ancient world's most enduring structures were not merely stacked, they were woven together. This mastery of joining hard stone points to one final, crucial element: the sophisticated tools they developed to make such precision possible. The granite workshop echoes with a rhythmic, percussive sound, the steady tapping of stone on stone. Here, artisans faced the ultimate challenge, shaping the hardest rock with tools that seem impossibly soft. Their 15th method was a quiet revolution in the innovation of specialized stone-cutting tools, each one designed for a specific, punishing task. To drill a hole through solid granite, they used no powered drill bit. Instead, they employed a simple copper or hollow reed tube. They would place the tube against the stone's surface, add a generous amount of wet quartz sand as an abrasive, and then spin the tube back and forth, either by hand with a bow-like device or by rolling it between the palms. The quartz sand, harder than the granite, did the real cutting, grinding away a perfect circular groove. As the tube wore down into the stone, it would leave behind a solid core which could be snapped out. This process created the remarkably precise, cylindrical holes we find in ancient artifacts, like the sarcophagus inside the Great Pyramid. The walls of that sarcophagus also show evidence of another brilliant tool, the stone saw. This was not a toothed blade like we use today. It was a large, flat sheet of copper, dragged back and forth across a granite block. Again, the magic was in the abrasive slurry of sand and water fed into the cut. This mixture turned the soft copper blade into an infinitely repeating, microscopic cutting edge, slowly grinding its way through the incredibly tough stone. It was a painfully slow process, but it yielded cuts of astonishing smoothness and precision. For shaping the granite itself, they turned to the hardest stone they could find, dolerite. They fashioned these into pounding stones, heavy hammers that could withstand the impact. The method was not about striking to break, but about pulverizing. A worker would systematically pound the surface of the granite block, reducing the crystals to a fine powder that could be brushed away. It was a technique of supreme patience, removing minuscule amounts of material with each blow. A modern stonemason who has tried to replicate this method describes it as a meditative, almost brutal exercise in persistence. You are not cutting the stone, you are defeating it slowly, grain by grain, through sheer, unwavering repetition. The time required is almost unimaginable to us. Dressing a single granite block to a smooth finish could take a single worker many months of constant, rhythmic pounding. This reliance on abrasion and percussion reveals a profound material intelligence. They understood that the battle was not won by the hardness of their metal, but by the even greater hardness of the sand they employed as their invisible, consumable blade. What does it say about a culture that would develop an entire suite of tools, not for convenience or speed, but for the singular purpose of mastering a specific, defiant material? This deep, intimate knowledge of stone properties was not just practical, it was a form of encoded wisdom, passed from master to apprentice in a lineage of skill that stretched across generations. That accumulated knowledge of materials would be useless, however, without an equally sophisticated system for managing the entire, sprawling operation from start to finish. Deep within the mound of Newgrange in Ireland, a narrow shaft aligns perfectly with the horizon. For just a few minutes at dawn on the winter solstice, a beam of sunlight pierces the darkness, traveling 60 feet to illuminate the innermost chamber. This was not a lucky accident. It is a precise, engineered event that occurs year after year, a silent testament to a 16th method, the profound role of astronomy in site selection and design. For ancient builders, the sky was not a distant mystery. It was the ultimate blueprint and the master clock. They planned their most sacred structures in direct conversation with the cosmos, using the predictable movements of the sun, moon, and stars to dictate everything from a building's orientation to the very timing of its construction phases. This field of study, known as archaeoastronomy, reveals that these alignments were both practical and deeply symbolic. The sun's path divided the year, marking the solstices and equinoxes. These celestial events were not just dates on a calendar, they were triggers for action. The summer solstice might mark the start of a quarrying season, while the winter solstice, like at Newgrange, could signify a time of spiritual renewal, a moment to connect the world of the living with the realm of the gods through architecture. This knowledge was power. It allowed a society to plan its agricultural cycle, its religious festivals, and its monumental construction with a rhythm dictated by the heavens. At Chichen Itza in Mexico, the stepped pyramid known as El Castillo becomes a serpent of light and shadow during the equinoxes. As the sun sets, triangles of shadow cascade down the northern staircase, merging with the stone serpent heads at the base to create the illusion of a giant snake slithering down from the sky. This was a dramatic public display of celestial knowledge, a fusion of astronomy, architecture, and mythology designed to awe and unify the community. Nearby, the strange, round structure called the caracol, with its narrow, slit-like windows, is widely believed by experts to have been an observatory. Its windows are precisely aligned with the extreme rising and setting points of Venus, a planet of critical importance in Mayan cosmology. A leading archaeoastronomer explains that tracking Venus over its complex cycles was essential for the Mayan calendar and their understanding of time itself. The building itself was a scientific instrument carved in stone. Perhaps the most debated celestial correlation is the one proposed for the Giza Plateau. The Orion correlation theory suggests that the arrangement of the three main pyramids mirrors the three stars of Orion's belt, while the Nile River represents the Milky Way. Whether this alignment was intentional or a compelling coincidence is still hotly debated among scholars, but it highlights a compelling possibility that the entire Giza necropolis was designed as a mirror of the heavens, a permanent echo of the pharaoh's celestial destiny. Look up at the night sky from your own home. What patterns do you see in the stars? If you were to build a monument that would last for millennia, what cosmic story would you choose to tell with stone? This celestial connection was far more than a technical trick for alignment. It was part of a holistic worldview that saw no separation between the earth and the sky, between a temple and a constellation, believing that harmony in one reflected order in the other. A citadel clings to a mountain ridge, its stones merging so completely with the living rock that it seems to have grown there. Machu Picchu is perhaps the ultimate expression of a 17th method, the profound harnessing of environmental and geological knowledge. The builders did not fight the mountain, they collaborated with it. They intentionally positioned the city's most important structures on outcrops of solid granite, using the natural contours of the ridge for both structural strength and defense. Every terrace, every wall was designed in concert with the land, not imposed upon it. This deep wisdom extended far beyond simple placement. The engineers of Machu Picchu understood the immense threat of landslides on such a steep, rain-drenched slope. Their solution was a masterclass in hydrological engineering. They constructed over 500 drainage channels that run through the site, lining the terraces with deep layers of crushed stone for filtration. When the heavy rains came, this system channeled the water away efficiently, preventing the soil from becoming saturated and sliding down the mountain. It was a system so effective it has kept the site stable for over 500 years. This principle of selecting the right foundation was a global constant. The Romans, for instance, were masters of material science. They discovered that by mixing lime and volcanic ash from the town of Pozzuoli, they could create a concrete that was not only strong but actually hardened and grew stronger when exposed to seawater. This specific volcanic ash, rich in minerals, reacted with the water to form crystals that locked the concrete together, creating the indestructible harbors and aqueducts that still stand today. Ancient engineers also mastered the flow of water through gravity. Across the ancient world, from the Inca to the Romans, aqueducts were designed with a precise, gentle slope. They channeled water from natural springs in the highlands, allowing gravity to do all the work of carrying it for dozens of miles to cities and construction sites. This required an incredible understanding of topography, surveying the land to maintain a consistent downhill grade that ensured a steady, reliable flow without pumps or power. These builders possessed an intimate, almost symbiotic relationship with their surroundings. They knew which way the prevailing winds blew, where the water table lay, and how the earth might tremble during a quake. They saw the environment not as an obstacle to be conquered, but as a partner to be understood. In our modern world of steel skeletons and land-leveling bulldozers, what profound lessons have we forgotten? Could our own structures achieve such longevity if we first learned to listen to the whispers of the landscape before we ever broke ground? The silent, brooding statues of Easter Island stand guard over an empty landscape. Their colossal forms a stark reminder of a society that pushed its limits to the absolute edge. Nearly 1,000 of these moai were carved from volcanic rock, with some weighing over 80 tons and standing 30 feet tall. Their creation and transport across miles of rugged terrain is one of history's most haunting engineering puzzles. How did a small, isolated population with no wheels or large animals achieve such a feat? The leading theories are as dramatic as the statues themselves. One compelling idea suggests the moai were not dragged but walked to their platforms. In this method, teams of rope pullers would rock the statue from side to side, using its own weight and a pivoting motion to make it appear to walk forward. It was a dangerous, rhythmic dance that required perfect coordination, a theory dramatically proven feasible in a modern experiment where an 18-ton replica was walked hundreds of feet by a small team. The more traditional theory involves a different kind of choreography, using a wooden sledge or a Y-shaped frame, gliding on a path of lubricated sweet potato pulp over log rollers. Both methods worked, but both consumed a society's most precious resource, its trees. The island's once lush palm forests were systematically cleared to make way for agriculture and to provide the rollers and sledges needed to move the moai. This massive environmental transformation had a cascading effect. Without trees to anchor the soil, erosion set in. Without large trees to build canoes, deep-sea fishing became impossible, cutting off a vital food source. The very act of honoring their ancestors by raising these giants ultimately undermined the society's ability to survive. An archaeologist who has studied the island's collapse for decades frames it as a tragedy of the commons. The islanders were likely competing clans, each erecting larger and more numerous statues to display their power and divine favor. In this escalating competition, no single group could afford to stop, even as the collective resource base crumbled around them. The lesson of Rapa Nui is not about a single catastrophic failure, but about a slow, relentless tipping point. Can a society's most profound expressions of faith and identity become the very instruments of its undoing? The fallen moai, lying abandoned along ancient roads, are a powerful testament to the delicate balance between monumental ambition and the fragile ecosystem that supports it. High in the Andes, the stones themselves seem to speak a silent language of geometry. The walls of Cusco and Ollantaytambo are not merely built, they are woven, with massive blocks of granite and limestone carved into complex, interlocking puzzles. The Inca approach to construction was born from necessity, engineered for survival in one of the most seismically active regions on the planet. A rigid, mortared wall would shatter in an earthquake, but an Inca wall dances. Its stones shift and settle against one another during a tremor, absorbing the violent energy, and then settle perfectly back into place once the shaking stops. This seismic resilience was achieved through one thing above all else, the pursuit of the perfect fit. So how did they achieve such impossible precision with only stone hammers and bronze tools? The technique was one of supreme patience and brilliant simplicity. To fit two stones together, masons would shape them roughly at the quarry. Then, they would position one stone above the other with a layer of abrasive sand in between. They would then repeatedly lift and lower the upper stone, grinding it against the one below. With each slight movement, the abrasive paste would wear away the high spots on both surfaces. Over countless repetitions, this process, a form of three-dimensional sanding, would slowly, inexorably grind the two stones into a flawless custom fit. The evidence of this is everywhere. Look at the famous 12-angled stone in a Cusco wall, a marvel of stonemasonry that fits seamlessly against its 11 neighbors. Each of its complex angles and facets was painstakingly ground to match the unique contours of the surrounding blocks. There was no standard shape, no simple rectangle. Every single stone was an individual masterpiece of fitting, a testament to a culture that valued the integrity of the whole structure over the speed of its assembly. This raises a profound question for our modern era of rapid construction. What is the true value of a single, perfectly placed stone, a task that might have consumed a craftsperson for an entire year? The Inca built for eternity, and their structures have outlasted empires. The most staggering aspect of this achievement is that the Inca had no written language. Their entire architectural genius, the complex knowledge of geometry, physics, and stonework, was transmitted without a single blueprint. This vast body of knowledge lived in the hands and minds of the master masons, passed down orally from one generation to the next through a relentless focus on practice and apprenticeship. A young learner would not read a manual. He would spend years watching, assisting, and finally, under a watchful eye, performing the sacred, grinding work himself. This was a living library of skill, where the only texts were the stones themselves and the only language was action. The sophistication of their results, achieved with the simplest of tools, stands as a powerful rebuke to our own assumptions. It proves that true complexity is not found in the tool, but in the thought, the patience, and the profound understanding of material that guides the hand. The Roman world was built upon a simple, elegant curve. While others stacked stone upon stone, Roman engineers perfected the arch, a shape that would carry the weight of an empire. An arch works by channeling force. The downward weight of the structure and any load above it is transformed by the curved shape, pushing outward and downward along the line of the stones. This outward thrust is then caught and contained by massive supporting walls or piers. This brilliant distribution of stress meant that Romans could create vast, open spaces, spanning wide rivers with aqueducts and enclosing colossal public arenas like the Colosseum without forests of interior columns. The arch was more than a structural element, it was a liberation of space. But this architectural ambition required a second, even more revolutionary invention, a magical kind of concrete. Modern concrete eventually crumbles, especially in seawater, but Roman concrete seemed to defy nature. Its secret was a specific recipe. They mixed lime with a special type of volcanic ash called pozzolana, named after the town of Pozzuoli where it was mined, and then added aggregate like chunks of rock and brick. When this mixture was combined with seawater, a remarkable chemical reaction occurred. One materials scientist who has studied ancient Roman samples explains the process. The seawater triggers a hot reaction, forming rare, crystalline minerals that interlock and grow over centuries. These minerals actually block microcracks from spreading, meaning the concrete self-heals and becomes tougher with age. This is why Roman harbors, pummeled by waves for 2,000 years, still stand as monolithic blocks while our modern versions deteriorate in decades. The ultimate expression of this material genius is the Pantheon in Rome. Its dome, cast in this phenomenal concrete, stretches 142 feet in diameter and rises to the same height. For over 1,700 years, it remained the largest unsupported dome in the world. The builders engineered it with a master's touch, making the concrete at the dome's base thicker and with heavier aggregate, then gradually thinning the walls and using lighter, porous pumice stone at the very top to reduce the overall weight. The result is a breathtaking, soaring space that feels both immense and impossibly light. This was not just construction, it was alchemy. The Romans understood material science on an intuitive level, proving that innovation was not always about moving bigger stones, but about creating smarter materials. The breathtaking longevity of their work forces a haunting question. With such a perfect, durable formula, why was this knowledge lost for centuries after their empire fell, leaving later builders to struggle in the dark? The fall of Rome plunged Europe into a long twilight, a period where the very knowledge of how to build on such a scale seemed to evaporate from human memory. This is the 21st method, the profound vulnerability of knowledge itself. Complex societies are intricate networks, and when they fracture, the specialized skills held within them can shatter and disappear. The most famous casualty was the recipe for Roman concrete. That miraculous, self-healing mix of lime, volcanic ash, and seawater was simply forgotten. For centuries, builders struggled to replicate its durability, their own structures crumbling while Roman aqueducts and harbors stood unshaken. The knowledge wasn't just misplaced, it was a casualty of a collapsed system. The vast supply chains for pozzolana ash broke down, the guilds of master engineers and architects disbanded, and the state sponsorship that funded such innovation vanished. A historian who studies these dark ages frames it starkly: knowledge is not a permanent possession. It is a fragile flame that requires a stable society to keep it burning. The same pattern unfolded after the collapse of the Great Bronze Age civilizations around the Mediterranean. The Minoans, for instance, were master hydraulic engineers with sophisticated plumbing and earthquake-resistant construction. When their palace society fell, those techniques faded, and later Greek builders started over with simpler methods. Why does this happen? Specialization is the key. In a thriving civilization, a master stone dresser spends a lifetime perfecting his craft, teaching his children, and working within a system that values his skill. When that system collapses, there are no more grand projects. The mason becomes a farmer to survive, and his unique, hard-won knowledge dies with him. It becomes a disconnected fragment, a story told by grandparents that sounds more like myth than manual. This forces a haunting reflection on our own world. We live in an age of unprecedented technological accumulation, but how much of it is truly secure? Our entire digital civilization rests on a foundation of complex manufacturing, global supply chains, and energy grids. If a major disruption occurred, how long would it take for the knowledge to build a microchip or maintain a power plant to become indecipherable? What advanced technologies do we possess today that might seem like magic or superstition to our descendants 1,000 years from now? The very existence of these ancient monuments, standing in mute defiance of the dark ages that followed their creation, is what makes them so haunting. They are the work of ghosts, the fingerprints of minds whose entire world of understanding has vanished, leaving only the stones to whisper of their genius. This eerie silence inevitably fuels our imagination, pushing us to wonder if their builders possessed secrets we have not yet rediscovered. The idea of alien architects is a seductive answer to these ancient mysteries. It is a theory that has captivated popular imagination for decades, suggesting that only visitors from another world could have achieved such impossible feats. Yet this line of thinking, while fascinating, fundamentally robs our own ancestors of their rightful legacy. The truth is, we do not need to look to the stars for answers when the evidence for human ingenuity is carved into the very stones before us. Mainstream archaeology, built on a century of meticulous excavation and analysis, provides a far more compelling narrative, one rooted in the tangible remains of these ancient societies. As one prominent Egyptologist who has spent his career at Giza puts it, The greatest disservice we can do to the ancient Egyptians is to deny them their own genius. Every time we point to a pyramid and whisper aliens, we erase the thousands of human hands, the generations of accumulated knowledge, and the breathtaking organizational skill that actually built it. The principle of Occam's razor guides this scientific approach. When faced with a mystery, the simplest explanation that fits all the available evidence is usually the correct one. Is it more logical to believe in an interstellar intervention for which there is not a single shred of physical proof, or to accept that human beings with patient observation, brilliant problem-solving, and immense collective effort achieved these wonders themselves? The evidence for human creation is everywhere once you know how to look. Take the controversial site of Puma Punku in Bolivia, often cited by ancient alien theorists for its precisely cut stones. The complex pitting and grooving on the andesite blocks are frequently described as laser-like cuts, but a closer examination by geologists and stonemasons reveals these marks are entirely consistent with human tooling. They match the patterns left by pounding stones and abrasive sand, the same slow, methodical techniques used across the ancient world. The H-blocks, with their precise interlocking joints, are masterpieces of carpentry translated into stone, a testament to a culture that understood woodworking and simply applied that knowledge to a more durable material. Why does our modern mindset so often leap to external, otherworldly explanations? Perhaps it is a symptom of our own technological age, where we are disconnected from the slow, patient power of manual skill. We struggle to conceive of a project spanning 50 years, so we invent a shortcut. We see perfection and assume it must require digital precision, forgetting that human hands, guided by generations of accumulated wisdom, are capable of their own kind of perfection. To attribute these structures to aliens or a lost super-civilization is to ignore the beautiful, incremental story of human innovation written in the archaeological record. It dismisses the very real, very human journey of trial and error, of failure and success, that led from the rough-step pyramid of Djoser to the polished perfection of the Great Pyramid. These monuments are not evidence of a helping hand from beyond. They are the ultimate signature of humanity itself, a declaration of what we can achieve when knowledge, will, and community are aligned toward a single, enduring purpose. The echo of ancient tools is being heard again, not in dusty tombs but in modern quarries and open fields. Experimental archaeology has become our most powerful time machine, a 23rd method where researchers abandon their textbooks to pick up ropes and stone hammers. This is not mere reenactment. It is a rigorous scientific process of testing hypotheses by physically recreating ancient techniques with period-appropriate tools and materials. The goal is simple yet profound: to separate what sounds plausible in a lecture hall from what actually works when your hands are raw and a multi-ton block refuses to budge. One of the most ambitious projects was led by archaeologist Mark Lehner and a team for a Nova documentary. They set out to build a small pyramid just 20 feet high, using only the methods available to the ancient Egyptians. They quarried the stone with dolerite hammers, they hauled blocks on wooden sledges, and they built an earthen ramp. The project was a success, but the true revelation was the sheer, unrelenting intensity of the labor. It proved the methods were feasible, but it also highlighted the astronomical investment of time and human effort. The team managed to quarry and move a 2-ton block, but it required a coordinated crew and took far longer than anyone anticipated. The experiment revealed nuances no blueprint could capture, like the critical importance of continuously wetting the path in front of the sledge to reduce friction, a detail straight from an ancient tomb painting, but only fully appreciated through grueling practice. On the other side of the world, another team tackled the mystery of the Easter island Moai. To test the theory that the statues were walked upright, they attached ropes to a concrete replica and, with a rhythmic rocking motion, successfully made the giant walk across the landscape. This dramatic experiment demonstrated that a relatively small team could maneuver an enormous weight with clever coordination and leverage. Yet the project leaders also encountered unforeseen challenges, like the statue's tendency to dig into the ground if rocked too forcefully, a mistake that could have shattered a real Moai. These hands-on trials provide something pure excavation cannot: a visceral understanding of the mistakes, the improvisations, and the intuitive problem-solving that must have been part of every ancient construction site. The archaeologists and engineers who lead these projects often speak of a profound respect that grows from the work. You stop seeing the pyramid as a static monument and start seeing it as a slow, relentless accumulation of daily triumphs and solved problems. What does this tactile form of learning teach us that 1,000 unearthed artifacts cannot? It reminds us that the greatest barrier to understanding the past is not a lack of evidence, but a lack of physical empathy for the skill, patience, and collective intelligence required. Each successful experiment closes one loop of speculation, yet often opens 3 new questions, proving that the story of how they built is a living narrative, still being written with every pull of a rope and every tap of a stone hammer. That same geometric intuition that stabilized pyramids now shapes our city skylines. Modern engineers, armed with supercomputers and advanced materials, are still guided by principles first proven in stone millennia ago. The legacy of these ancient builders is not locked in the past. It is a living library of solutions that continue to inform how we build for the future. The fundamental importance of a stable foundation, a lesson the Egyptians learned leveling the Giza Plateau and the Inca mastered by anchoring Machu Picchu to bedrock, is now a non-negotiable first step for every major construction project today. We simply use laser levels instead of water-filled trenches. The sheer mass and geometric stability that gave the pyramids their eternal form find a direct echo in our most massive modern structures, from gravity dams that rely on their own immense weight to hold back reservoirs, to the broad, pyramidal bases of modern skyscrapers designed to resist wind and seismic forces. This is not coincidence, it is the enduring logic of physics, first discovered through patient physical trial and error. Perhaps the most urgent ancient wisdom we are relearning comes from the Inca. Their polygonal, mortarless walls, which danced during earthquakes, are now a subject of intense study for engineers in seismic zones like Japan and California. Researchers are analyzing how these interlocking stones dissipate energy, hoping to translate that ancient flexibility into modern, life-saving building codes and designs. The architect Frank Lloyd Wright, for instance, was deeply inspired by the way Japanese temples used interlocking joinery to withstand tremors, a principle he admired in pre-Columbian structures as well. He saw in these ancient forms a timeless dialogue between design and the environment. The longevity of these structures provides something no laboratory test can replicate: real-world data on material durability spanning thousands of years. Scientists studying the chemical composition of Roman seawater concrete are not just historians. They are material scientists seeking clues for creating more sustainable, self-healing building materials for our own era. The next time you walk through a city, look up. You might see the ancient principle of the arch in a bridge support, the logic of mass in a dam's profile, or the wisdom of a stable foundation in every building that stands tall. The true legacy of these builders is a profound reminder that the most elegant solutions are often not invented, but rediscovered, standing as a timeless testament to human ingenuity. Even with all our discoveries, the Great Pyramid still guards its deepest secrets. We have mapped its chambers and theorized about its ramps, yet the exact step-by-step process of its assembly remains one of history's most tantalizing puzzles. The sequence of placing over 2 million blocks, the logistics of feeding and housing thousands, the final breathtaking act of setting the gleaming capstone at nearly 500 feet, these are details no ancient text has handed down to us. Each proposed answer only seems to birth new, more intricate questions. Across the globe, the foundation of the Baalbek Temple in Lebanon presents another colossal enigma. How were 3 limestone blocks, each weighing over 800 tons, quarried, transported, and positioned with such hair's-breadth precision? The sheer weight defies even our most confident modern explanations. These are not closed cases but active investigations, and the tools of discovery are now more powerful than ever. Archaeologists are no longer limited to trowels and brushes. They now peer inside solid stone using cosmic rays. A technique called muon tomography detects these naturally occurring particles that pass through matter, revealing voids and hidden spaces just as an X-ray would. This is how, in recent years, scientists announced the discovery of a large, previously unknown void deep within the Great Pyramid, a hidden chamber that had escaped notice for 45 centuries. Its purpose remains a complete mystery. From the jungles of Central America, LiDAR technology fires laser pulses from aircraft to strip away the dense canopy, revealing entire lost cities and road networks carved into the earth below. Ground-penetrating radar scans the soil under our feet, mapping buried walls and foundations without ever breaking ground. These technologies are rewriting the story of ancient civilizations in real time, proving that our maps of the past are still full of blank spaces waiting to be filled. With every scan and every new void detected, we are reminded that these monuments are not fully known. They are still giving up their secrets. If you could choose one ancient mystery to be solved by this new technology, what would it be? Would you want to see what lies inside the newly found chamber in the Great Pyramid, or finally learn the method used to move the stones of Baalbek? The field of archaeology is no longer just about studying what is already visible. It is about listening for the whispers from hidden chambers and reading the stories still buried in the earth, ensuring that the final chapter on these ancient builders is far from being written. A single name, Amun, is carved into the stone of a pyramid block, a quiet signature left by a worker thousands of years ago. Behind every megalith and every perfect joint lies the 26th and perhaps most profound method, the immeasurable force of human skill, patience, and collective will. These structures are not merely monuments to pharaohs or gods. They are eternal testaments to the unnamed millions whose hands shaped the world. We see the fingerprints of the stone dresser who spent a year perfecting a single granite block, and the calloused hands of the rope puller who hauled in rhythm with 100 others. The true wonder is not just the engineering, but the society that could align so many individual lives toward a single generational goal. In the Egyptian quarries, we find the proud graffiti of work gangs who named themselves the Friends of Khufu or the Vigorous Gang. These were not anonymous laborers, they were teams with identity and camaraderie, taking visible pride in their contribution to something eternal. The knowledge required was not stored in books, but passed from a master mason to his apprentice, from a father to his son, in a living chain of learning that stretched across centuries. A historian who has dedicated her life to studying these workers reminds us of their humanity, saying that when we look at these stones, we must see the people. They laughed, they got tired, they felt pride in a day's work, and they dreamed of their families just as we do. They were not a different species of superhuman, they were us, armed with an extraordinary degree of focus and a shared belief in their purpose. This reflection forces a question into our modern, fragmented world. What could our global society achieve today if we were to channel our collective intelligence and resources with that same unity of purpose, that same generational patience? The pyramids and the Great Walls stand as a challenge to our own potential, asking us what monuments to human collaboration we might yet build for the future. The quarries are now silent and the ramps have long since returned to dust. Yet the stones themselves tell the final, most compelling story of all. We have journeyed through the evidence, from the patient grinding of granite to the celestial alignment of pyramids, and a clear truth emerges. These were not miracles or the work of outside forces. They were the achievements of master engineers who leveraged the fundamental principles of physics, the power of their environment, and the incredible potential of organized human communities. They looked at a cliff face and saw a pyramid. They looked at a river and saw a highway. They looked at the stars and saw a blueprint. The key takeaway is as simple as it is profound. Human ingenuity, when fueled by shared purpose and relentless determination, is the most powerful tool ever devised. These colossal structures are not alien relics. They are the enduring signature of our own ancestors, a permanent memorial to what humanity can accomplish when knowledge, will, and thousands of hands are aligned toward a single generational goal. Let their achievement stand as an inspiration. The challenges we face today, from engineering sustainable cities to exploring the cosmos, demand that same blend of creativity, patience, and collective resolve. We have done the impossible before. We carry that legacy in our very bones. We would love to hear which ancient mystery captures your imagination most. Is it the moving of the Moe, the secrets of the Great Pyramid, or the polygonal walls of the Inca? Share your thoughts in the comments below. If you enjoyed this journey into the deep past, subscribe for more explorations into history's greatest enigmas. The stones have spoken, and their story is one of unparalleled human achievement.